In this video, I'd like to address this question. What makes molecules stick together in the liquid and solid states? Let's take a look at an animation. In this animation, we can clearly see that molecules presented by the blue dots stick pretty closely together in the solid state and the liquid state. And the question is, well, what makes them do that as compared to molecules in the gaseous state where they're pretty far apart and there's essentially no interaction between them? Here's an answer. There are intermolecular forces, or sometimes called intermolecular attractions, among molecules. And this is essentially the sticking power between molecules that keeps them in the liquid or solid state. Intermolecular attractions arise because of weak electrostatic attractions between molecules. Electrostatic attractions occur when an electrically positive region is attracted to an electrically negative region. So-called dipole exists in each molecule. This cartoon can be an example of a speck of solid. Each oval represents a molecule. In each molecule there exists a dipole, a region of positive and a region of negative. And notice how the molecules are oriented in the speck of solid. The positive end of one molecule is attracted or lined up with the negative end of another molecule. And this continues throughout the speck of solid. Asymmetrical distribution of electrically positive regions and electrically negative regions, i.e. dipoles, are inherent in polar molecules. Hydrogen fluoride and water are two examples. There are Lewis structures of HF and water, and below each Lewis structure is something called an electrostatic potential map. These maps show electrically positive regions and electrically negative regions. Using electronegativity values, we could predict where the electrically negative regions would reside in a molecule. The symbol that is used to show where the dipole exists in the molecule. The arrowhead points towards the electrically negative region, and the cross, or the other end of the arrow, resides in the electrically positive region of the molecule. In addition to arrows with crosses at the other end, these delta symbols can also be used to show where the electrically positive and the electrically negative regions are in the molecule. Symmetrical distribution of electrically positive regions and electrically negative regions, i.e. no dipole, are inherent in nonpolar molecules, such as BF3 and CH4. Next to each Lewis structure is the electrostatic potential map for the molecule. Notice the electrically negative region symmetrically placed in the BF3 molecule, and boron in the center is the electrically positive region. In CH4, carbon and hydrogen have very similar electronegativities. There isn't too much localization of either electrically positive or electrically negative regions in the molecule. Well, a question could arise: if dipoles are needed for electrostatic attractions between molecules to keep them together in the liquid and solid states, then how do nonpolar molecules, those without a dipole, stick together to form liquids and solids? Nonpolar molecules will induce dipoles on other nonpolar molecules. What also can occur is polar molecules will induce dipoles on nonpolar molecules. We'll see this in the animations that follow. The first kind of intermolecular attraction I'll explain is induced dipole-induced dipole. This occurs among nonpolar molecules. One molecule will induce a dipole on another molecule. In the molecule that is doing the inducing, a dipole in fact is created in that molecule. To summarize induced dipole, molecules do not need to be polar. An example of two nonpolar molecules would be two nitrogen molecules. And of the intermolecular attractions I'll present, induced dipole is the weakest. The next type of intermolecular attraction is dipole-induced dipole. This occurs between a polar molecule, which has an existing dipole, and a nonpolar molecule, which does not have an existing dipole. The polar molecule induces a dipole on the nonpolar molecule. A very common example is water and oxygen. Oxygen remains dissolved in water because of the water inducing a dipole on the oxygen. To summarize dipole-induced dipole, one molecule needs to be polar, the other molecule nonpolar. An example, water and oxygen, and this intermolecular attraction is also considered weak. Next is dipole-dipole. I have the word regular underneath the title dipole-dipole because there is another type of dipole-dipole attraction that involves hydrogen bonding. We'll see that next. But regular dipole-dipole involves two polar molecules that will not engage in hydrogen bonding. A good example is HCl. For ordinary dipole-dipole, both molecules need to be polar. And because of this, there's an increase in strength in the intermolecular attraction. Many molecules that undergo dipole-dipole intermolecular attraction undergo a specific type, which is called hydrogen bonding. In order for a molecule to engage in hydrogen bonding, a hydrogen on one molecule must be covalently bonded to either a nitrogen, oxygen, or fluorine atom. That hydrogen atom that is covalently bonded to the nitrogen, oxygen, or fluorine will hydrogen bond to a nitrogen, oxygen, or fluorine on another molecule. This is an electrostatic attraction, where the hydrogen is slightly positive and is attracted to the slightly negative nitrogen, oxygen, or fluorine. Here's an example of two alcohol molecules engaging in hydrogen bonding. Note the yellow line between the hydrogen and the oxygen is not a covalent bond. That simply shows the electrostatic attraction between the hydrogen and the oxygen. But I want to point out that the hydrogen that is engaging in this electrostatic attraction is covalently bonded to an oxygen. And the hydrogen is electrostatically attracted to the oxygen, which is on another molecule. Here's an example of water hydrogen bonding with an alcohol molecule. We could see the hydrogen that is covalently bonded to the oxygen on the alcohol molecule is electrostatically attracted to the oxygen on a water molecule. Here's an example of water hydrogen bonding with an ammonia molecule. The hydrogen of the water molecule is electrostatically attracted to the nitrogen of the ammonia molecule. Here's another example of hydrogen bonding in a DNA molecule. Notice the hydrogen bonding between the nitrogen and the hydrogen, the oxygen and the hydrogen. And the last intermolecular attraction we'll look at is ion dipole. This occurs between an ion, whether a cation or anion, and a polar molecule. Notice how the anion is attracted to, in this case, a water molecule. And notice the orientation of the water molecule. The hydrogens of the water molecule are slightly positive, and those are pointed towards the negative anion. When a cation engages in ion dipole attractions with a water molecule, notice how the water molecule is oriented towards the cation. The oxygen is pointed towards the cation because the oxygen is slightly negative. This table summarizes all of the intermolecular attractions that were covered in this video.